All right, so today there's two things that I want to cover for sure, and then maybe we'll do a little more beyond that. And those two things include this exercise 4 in the second assignment, and then also loops. So I think what we'll do is start with exercise 4, then we'll talk about loops. So here it is, exercise 4. Write a console program that converts meters into feet and inches. The program starts by asking the user for a measurement in meters, and the program should accept a floating point number. After getting the number, the program computes the number of feet and inches equal to the specified number of meters. The program outputs feet and inches as whole numbers. The program should round the number of inches correctly. Test that your program produces the following outputs for the given inputs. So this is lab 2, and this will be what you do in the lab. So I've got a 201 folder here. And I should have a lab 1 folder, so I'm going to make directory lab 1. Use ls to see what I did. And I also want to make a directory for lab 2. And this main program here is part of, let's suppose it's a part of lab 1. And I'm going to move that into lab 1, into the lab 1 folder. That's how you move it. So you'll see it's not there anymore, but it's in lab 1. So I can ls lab 1 to see that main is in there. So just a quick review of some of the commands you need to have a working knowledge of in the lab. So here we are. We don't need a.out. I'll remove that. So I use ls a lot just to see, make sure everything's good. And now I'm going to copy out of lab 1 the main.cpp file, and I'll copy it into lab 2, but I'm going to give it a name. I'm going to call it ex4.cpp. Then I'll cd into lab 2. Here I have ex4. And this is more than we need. We don't need cmath. And I'm just going to do this. Just to test to make sure that what I have, my starting point, I can compile. There it is. Now notice that I have this indented. That's because this statement, it's a statement, it ends in a semicolon. Most statements do. They end in a semicolon or a closing brace. And this statement is a part of the main function. This is the start of the main function. Because the statement is within the main function, I indent it. So I'm using tabs here to show an indent. If you're going to indent using tabs, then use tabs everywhere for indentation. Don't mix tabs with spaces. See, if I space this out, now here I'm using spaces for this indent, and I'm using a tab for this indent. But it looks good only because my tab stops are set at 8 spaces. But if I set the tab stops to 4 spaces, then it wouldn't look right. But you don't know who the other person who may read your code, like Jaron or me, for instance, in this class. You don't know what our tab stop is set at. So the way to play it safe is to only use tabs or only use spaces. Don't mix them, because you don't know the other person what their tab stop is going to be set at. So what we need to do is read in the number of meters and convert it to feet and inches. Let's see how to do that. We'll just prompt the user for the number of meters, and then we'll read it in. Now it's going to be a floating point value, so we want to accept decimal points. So we declare the variable meters as a double precision floating point number. And we use the standard input stream with the input operator and read a value into meters. And that should compile. Meters equals. There we go. Now we want to convert this to feet and inches. So we're going to do something here, do some calculations, and then we're going to print the result. So we're going to say, we're going to do it something like this. We're going to have whole numbers. We're going to have the number of feet. I'll say that's going to be 2. And the number of inches, say that's 3. That's just test data. And then we're going to print out the number of feet. Maybe I'll do it like this. And the number of inches. I did that all in one line. There it is, 2 feet 3 inches. So 1 meter is 2 feet 3 inches, which is not right, but this is our test data. This is, see, I'm just getting the skeleton done, just the outer shell of the logic. I want this working, and it helps me focus on what I need to do. I need to compute 2 integer values. We're inputting a double value, which we're storing in meters. Then we have to calculate 2 integer values, the number of feet and inches. All right, now we have a test data there. We see how the program is supposed to look. So let's figure out how to do it. Now for the feet, we can use what's called integer division. We can take the number of meters and divide by feet per meter. How many feet are in a meter?
3 feet 3 inches.
This number here?
Yeah. 3.2.
But normally we would do something like this. We would have a constant here. Constant, that's feet per meter. And I'll set it up there. And that's a double, by the way. Here's the use of that const keyword here. So this provides, in case we want to use the value more than once, it also provides documentation for us. So we take meters and divide by feet per meter, then we get the number of feet. Notice this is a double. This is a double, and this is a double. So this is double precision. This is floating point division. But when we try to store it in an integer, then we get truncation. So 1 meter is how many feet? 2 or 3?
3.
3 feet or 2 feet? I mean, truncated, not rounded.
3 feet.
3 feet? It says 0. Let me do this. I'm going to change this to a double. Let's make feet a double so we don't get truncation. One meter is 0.3 feet. We got that wrong, right?
Yeah.
Yeah. This should be a multiplication. Three. You got it. So it's 3.28. But look, what we're going to do is truncate. So I'm going to declare this an int. So now we can't put a floating point number in an integer storage space. So the computer's going to do something. It's going to drop off the decimal component. There it is, 3 feet. Well, the 3 inch, that's our test data, 3 inches there. All right, so that's the easy part, the feet. Well, what about the inches? Well, I've done this problem many times, so I'm just going to show you the answer here without going through. I don't know. I don't remember how I figured it out. We can do it like this. Maybe I'll do it in pieces, maybe to make it easier to understand. So I have a double value. This is the total meters in inches. That's going to be meters. How am I going to do that? Yeah, maybe I'll do like, we do it like this. Well, I'm going to use the same value I used up here. So this is the total meters in feet. And the total meters in inches is just that times 12. Maybe I should make this kind of symmetric here. So I'm going to go double. I'm going to do it like this. I'm going to make it easier to understand. I think we'll try to make it easier to understand. Total meters in feet. It's just meters times feet per meter. The total meters in inches is the total meters in feet times 12. There we go. So we have the total meters represented in feet and total meters represented in inches as floating point numbers. So get the to get the number of feet as a whole number, what we do is we just try to cram in this value into that ft variable. And for the inches, let's wait on that. I just want to check this logic first. We should come up with 3 again when I type in 1. At 3 feet. And to see what I'm doing, see how I'm crafting this thing? The code is changing a lot. This looks a lot different than when we first started, right? So this is how you program. You got to rename things, move things around. You almost never just write it out straight. It's like crafting. It's kind of like pottery. You kind of work it and get it into some nice shape, something that makes sense. So now, the inches. We're going to take the total meters and inches, and we want to take out the number of inches that have gone into here. So in our case where we're typing in 1 meter as an input, we're coming up with 3 feet. So we want to take out 36 inches from our total meters and inches value. Three feet, 3 inches. 3 feet, 3 inches. What about 2 meters? 6 feet, 6 inches. Oh, the problem there is we need to round up because the fractional part of the inches is bigger than 0.5. Well, we're truncating in our program now. We need to round it up to 7. So I'm going to show you the trick for rounding up numbers in all languages, not just C++, but in all the languages that I've ever seen. There's one simple way to do rounding. I'm going to tell it to you. Here's the secret. Try not to forget this. Just add a half. That's it. Because remember, you're truncating. You're dropping off the fractional part. So if you're above 0.5, adding a half will bump you up to the next integer value. And then you truncate and you drop off the decimal stuff. Oops, I'm going to try 2. 6 feet, 7 inches. And let's try this number here. 1 foot, 0 inches. Got it. We got the test data running. So that is one way to do this exercise. Doesn't seem that hard, does it? Did anyone try to do this? How long did you spend on it?
About 20, 25 minutes.
How many minutes?
About 20, 25.
25 minutes? Did you get the answer? Oh, that's great. Anybody else?
I didn't get the answer.
You didn't get the answer, though. Not yet, so it's going to keep going. Over there?
I was stuck on rounding it.
Stuck on rounding. Well, it's so simple. Add a half. You got that. Okay. So there's a lot of variation, actually. Sometimes when I try to tackle what I think is a simple program, that'll take me a day. Other times it'll take me 10 minutes. There's a huge variation. And it's the 10-minute version. The 10-minute program I built isn't any more lines of code than the 1-day program. There's just a lot of variance when it comes to amount of time taken to code things. All right. Now, what I want to talk about is loops. How to write loops. How to read loops and understand them. You'll see in this exercise here, exercise 2, this is a simulated test. Here's a loop. This is called a while loop here. And this is the whole loop statement right there. I've highlighted the entire loop statement. That's one statement. It has substatements, but it's viewed as a statement. Even though it has subcomponents, it's still a statement, one statement. There's 2 statements here. This is the first statement, and this is the second statement. The second statement happens to have 2 substatements, but you should see it as 1, 2 statements. Here's another loop. This is called a for loop, and these are the only 2 type of loops that we're going to look at. There's also a do while loop. that we're going to skip over. We're not going to do that one. The while loop is sort of a primitive, basic loop. That's your standard beginning loop. And then the for loop is sort of a more compact way of expressing a while loop, which is, and this for loop is appropriate in certain situations. And in other situations, the while loop works better in terms of producing easier to read code, not faster running code, easier to read code. And the ease of reading code is usually more important than faster running code. Most of the time, the issue and the importance, the critical issue is the readability of the code and not its performance. Normally, that is the case. I would guess more than 95% of the time, in a professional context. Because if the code is not readable, you've got 100,000 lines of unreadable code. You just got hired on a job, and your job is to change the program to do something different. How long is it going to take you to make that change? If the code is neat, if it's readable, if it's well structured, it's logical, it expresses its logic and its function clearly, that programmer can get that job done a lot faster. And that's a lot of money. What does a programmer make? $70,000 a year to begin with? 100,000, 150,000. So that can be expensive at programmer time. So readability of code is a very important issue, and that's a focus in this class. We want to, when you submit your work to Jared and me, the code should be organized nicely. It should be indented correctly. It should be logical. It shouldn't have extraneous statements in there that don't contribute to the functioning of the program, and so on. So that's a little side trip there down that road. Well, let's get back to loops now. Let's just play around and talk about how loops work. So I'm just going to make a copy of this program. And let's see how this works. So here's a loop. While true. So this is a loop condition. We'll do it like this. While 3 equals, I'm going to do it differently. Watch this. Let's declare an integer, I, and set it equal to 3. And this is while I equals 3. Well, I equals 3, we're going to do something. We're going to input I. So we have this loop. What a loop is, see how I've indented these two lines? And this is the closing brace here. This is the opening brace. The substatements are indented. The substatements are included between the opening and closing braces in this syntax. So I have the word while. So that means something's going to get repeated. And we're going to repeat the substatements while this condition, this expression evaluates the true. So what the loop does, what the system does, what the computer does is it says, okay, I'm going to look at this when it hits this statement. This is a whole statement right there. It's one statement. This program has 2 statements. This is the first statement. This is the second statement. When the first statement finishes running, then we run the second statement. When the second statement finishes running, we exit from the main function. We're done. We do 2 statements in this function. Now, the second statement happens to have substatements. But we're ignoring that when we're zoomed out and looking at the top level. We're ignoring those substatements. We're just saying we got one statement and then a second statement, and then we exit main. But if we zoom in and we say, oh, okay, let's just look at how this one statement runs. This one statement is a complex statement, and it's got these two substatements, and it's going to repeat these two substatements as long as this expression, I equals 3, evaluates to true. So this is how it works. When the program runs, we're going to create a variable I, initialize it to 3. And then we're going to hit this loop, and it's going to say, oh, I'm going to repeat some substatements. Let me see if I want to repeat it all. So I'm going to say, all right, and I'm just thinking like the computer now. Is I 3? Yes, I is 3. Okay, then I'm going to run these. I'm going to print input I, and then I'm going to wait for the user to enter in a number. When the user enters a number, I'm going to write it into the variable I. And now what am I going to do? I'm going to go back to the loop condition. I'm going to reevaluate the loop condition. If the user typed in a 3, the loop condition remains true. When the loop condition is true, we're going to repeat those two statements again. We're going to keep repeating those statements each time we reevaluate the loop condition. But as soon as the loop condition becomes false, when the loop condition becomes false, then this compound while statement has finished executing. Now we go on to do the next statement, and there is no next statement, so we simply return from main. All right, let's look at that. What am I doing?
Still compiling the
I'm
example.
doing the wrong program. All right. Input I, 3, 3, 3, 3, 4. What's it going to do?
Go back to latitude $sign.
Terminates. Because 4, when we entered in 4 here, and then we came up to evaluate the loop condition, 4 does not equal 3. Now the loop condition is false. That means the loop statement has completed. When the loop statement completes, we do the statement following the loop statement. Well, there is no statement following the loop statement, but so that means we're done. We're finished with the program. But if we did have a statement there, we would run that statement. Let's just verify that. Three, 3, 3, 3, 3, 3, 4. Okay. See, so when the loop condition becomes false, the loop statement is finished executing. And we do the next statement. Now we have 3 statements. We have 3 top-level statements. Make careful note of the indentation. You need to indent your programs like this to show this logical structure. You know, when you have a relationship between, a substatement and a parent statement, you have to indicate that with an indent. All right. How about the following problem? Let's print 100 random numbers. Let's print 100 random numbers. Look at this, while true. See, this is an expression that always evaluates the true. Let's change that. That's an infinite loop. Okay, so while I is less than or equal to 100. Let's print 100 numbers. Let's print, 1 to 100. No, let's make it simple. 1 to 10. Huh?
So wasn't that 101 numbers now?
Well, I'm starting at 1 here. Yeah,
okay.
I'm getting there. I'm getting there. It's good you're thinking about that. So we start at 1. And while I is less than or equal to 10, we're going to print I. Oh, what's this program going to do?
It's going to give you numbers 1 through 10.
No. What's it going to do?
Just print a bunch of ones, right?
Print a bunch of 1s. How many 1s is it going to print?
10.
How many ones is that going to print?
10.
It's a trick question, okay? I'm going to warn everybody. You got it right. How many is it going to print? More or less than 10? You don't know how many? Not more than 10? You got to have a hypothesis here. Like the loop is going to repeat as long as the loop condition is true.
I is always one in this situation, isn't it?
I is always one. Loop condition is always true. So how long will the loop run?
It's a broken code forever.
It's broken code. It's going to run forever. That's called an infinite loop. There you go. It's like, you know, when your video game crashes, it's like, what's it doing? It's stuck probably in an infinite loop. Or it could be what's called a deadlock. The two things trying to get the same thing, you know, that sort of thing. I don't want to get into deadlock, but it's it could be an infinite loop. You got to shut down that game. Start it again. All right, so what we need to do here is,
You have to put in a statement that changes I.
that's right, we need a statement that changes I. Here's a statement that changes I, it increments I. We're going to advance to the next I. Now what's it going to print?
This guy count.
Yeah, what is it going to stop at? 10, yeah. All right, let's do that. There it goes, 1 through 10, okay. Now, maybe we don't want I, maybe we want a random number, all right?
Don't you have to see the random number generator?
Yeah, we do. We should see the random number generator. And I'm going to show why. Let's not do it and see why it's a bad idea. Okay, rand is a function. Here, I'm calling a function. When you call a function, you have the function name followed by an open parenthesis, 0 or more arguments, and a closed parenthesis. Well, we have 0 arguments, so we just have an open closed parenthesis. And this function, it's an expression just like all the other expressions. It's like 1 plus 2, that's an expression. 1 plus 2 evaluates to 3. Okay, when I say evaluates to 3, I mean you can think of it as being replaced by 3. An expression, 1 plus 2, will be replaced by 3 when the program runs. Rand will be replaced by a random integer when the program runs. Rand evaluates to, Rand returns. So we use all different kinds of language, but they all mean the same thing. I'm going to repeat it, a description of what Rand does here, in at least 3 ways, and they're all saying the same thing. Rand returns a random integer. Calling Rand evaluates to a random integer. This expression, where we're calling Rand, is replaced by a random integer when the program runs. So I'm just all describing the same thing. You can latch on to one of those things and catch the meaning, and then just copy that meaning onto the other expressions. Okay. All right. So let's see how this works. Those are called pseudo-random numbers. They're not true random numbers. If we run the program again, we get exactly the same sequence. So it's a sequence that looks random, but it's not because it's predictable, right? We get the same thing every time I run the program. So we want to make it a little less predictable, and so what we do is we have to tell this random number generator, this built-in random number generator, we need to pass in what's called a seed, which is some integer that it uses as a parameter to mix up, what it's going to do. So it's going to give us hopefully a different sequence for different seeds, although some seeds might produce exactly the same sequence. But I'm not sure. So it's called srand, seed the random number integer. We're going to pass in a 3. That's our seed value. So by the way, this srand and rand on the Linux systems in the lab, you might need to include C standard live. You know, with Xcode, I don't need to do that. So it's kind of non-standard where these functions are declared. So you might need that with your compiler. So let's pass in 3 as a seed to the random number generator. Notice I didn't do it down here. This is not a good idea. And what's that going to do? It's going to give us 10 numbers that look like what? Huh? Who can guess what the 10 numbers? Well, I'm going to guess, and I'm going to guess with 97% confidence. Because I get stuff wrong, you know. So I'm always a little hesitant to make an absolute declaration that, you know, what my guess is going to be is correct. What do you think it's going to print, based on what I've said so far? It's going to print 10 something, right? It's going to print 10 integers. What are the integers going to look like?
3-digit numbers.
3-digit numbers?
The same 3 numbers repeated?
Huh?
The same 3 numbers repeated?
The same number, no, not 3 numbers, the same,
It's gonna be the same number.
same number.
10 times.
Well, that's what I think, okay? I'm saying that's at 97%. All right, are we ready to try this? Everyone's done thinking about it?
So every time you see the random, it's gonna stop its randomization and start over.
It's going to reset it to the same sequence. Remember, you pass in a number to srand, you're setting the sequence. So you're resetting the sequence back to the same sequence over and over again. But you know, now I just dropped my confidence down to 90%, maybe 85. I'm starting to, I can see maybe if you already start calling rand and when you reseed, maybe it doesn't set the sequence back to the beginning. You see, I'm starting to doubt it a little bit, but let's see. Let's see what happens here. Ah, got it. 100% confident now. Yeah, we're resetting the sequence back to the same thing. So what we want to do is seed it outside of the loop. We only seed it, generally, when you have a random number generator, you only seed once, at the very beginning of your code.
What is the significance of the 3 in this round?
There's no significance to the 3. I just have a habit of using 3 in my lectures for some reason, and I don't know. But look, we get the same sequence over and over. That's because the 3 is the same 3, right? So we want to change that. We want to pass in something that varies a little bit. So time is a function that returns, if you pass in 0 to this time function, it returns the number of seconds that have elapsed since some epoch, some point in the past. Usually it's January 1st, 1970, you know, 0 hour. So this will change, this value here, time 0, will produce a different number every second. So if we run the program quickly twice, we're going to get the same number. Look at that, I got 2. Look at that, random within the same second. Oh, it's not working.
You didn't recompile?
I didn't compile? Oops. All right, there's one run, there's another run. Oh, that's different. I was just, it looks similar. That's
not
just,
doing it fast enough.
well, no, look, it's these digits here are different.
Well, because the second change.
See that? They look similar, but they're different. I was just, look at these are matching exactly. 1883, 1883, 18831. These match exactly. So see, it's a pseudo-random number generator. It's it's got some predictability built into it. That's why you don't use this when you do encryption. You know, encryption, you know, like when you do a credit card transaction, you purchase something online, and you see HTTPS in the browser, the URL, and your communications are being encrypted, so no, a third party can't spy and get the data that you're sending. That all relies on random numbers. And if the random number were generated using this program, you'd all have your accounts drained, because that wouldn't work as a good encryption procedure. Encryption needs to relies on the fact that you have a very good random number generator, as close to real as you can get. And this is far from real. And you can see that right here in the first number. It's so close to each other. And that shows that there's a weakness in there. All right, so anyway, that's that. And I do want to say another thing here, that normally what you see, you don't see a programmer use this form normally. You usually see an index starting at 0. As a computer, it starts counting from 0. It doesn't count. It's not like a human that starts counting from 1. When I count things 1, 2, 3. Computer says 0, 1, 2, like that. So we start at 0, and we want 10 things exactly. That means we need to stop at 10 and not do it at 10. So 9 should be the last index value that we act on. So we start it. We act when I is 0, we act when I is 1, we act when I is 9. That's 10 actions. See, it's harder to read like this, for a human. But when you become a programmer, if that's what you end up doing, then this will be easier to read, because that's how most code is written. Because most code is ultimately sort of tied back to the hardware, and that's how the hardware works. So this should give us 10. Oops. And I think that's done. Now this is called the while loop. And here we're running a loop exactly a known number of times, 10 times. We're running this loop 10 times. We just want to repeat something 10 times. So this is a very simple loop. And so for this type of loop, it's more appropriate or more common that you see a for loop used. Because a for loop is a little more compressed. Let me show that to you. This is the code that we have, and I'm going to comment this out. That's a multi-line comment. See, this is an opening comment. It's a closing comment. All the lines in between the opening and closing symbols are considered comments and ignored by the compiler. I commented that out. How does this loop look as a for loop? Well, this is how you do it. It's for, then you have 3 sections. You have a first section, a second section, and a third section. You have these 3 kind of regions in this loop. And then you have the opening and closing braces. And in between the opening and closing braces, just like the while loop, are the statements that you need to repeat. So this is how you repeat something 10 times up here with a while loop. Now, how do you repeat something 10 times with a for loop? Well, we're gonna use an index variable just like the while loop, but we're going to put it in this first section. And this first section here is called the initialization statement. So this is I think you can only have one statement in there, I think. And so here we do, and this runs once. When the for loop runs, once again, this is a single statement viewed from the bird's eye view. This is a single statement, but it's a complex statement, does many things. The first thing it does is it creates a variable I, initializes it to 0. Then the second thing it does, just like the second thing it does is it evaluates a loop condition. So you have to have a loop condition. All the different loops have loop conditions. They don't all have indices or integer variables like this, but they all have loop conditions. The loop condition is what goes in the second spot. And the loop condition is that I is less than 10. So when we run this for loop, the first thing we do is create an I, initialize it to 0, and then we evaluate the loop condition. If the loop condition is true, we do the statements that are the substatements. And then after we've finished running the substatements, then we do the end of loop operation, which is the third section of the for loop. And the end of loop operation is to increment I. So this is the operation that's done at the end of the loop. See, in the while loop, we just put the increment of I at the bottom of the loop. But for the for loop, we just put it in this third section. It's done at the end of the loop. Just like the while loop has a loop condition, well, the for statement has the loop condition in the middle section here. And then there's some initialization. This is the only thing that's not repeated. The loop condition is repeated. The end of loop operation is repeated. The substatements are repeated. The only thing that's not repeated in a for loop is the initialization, which is right here. All right, let's see this. There we go. So these are equivalent. Now do you see, look at this. This is 3 lines of code. 1, 2, 3. See, it's more compact. And this is 1, 2, 3, 4, 5 lines of code. So we eliminated 2 lines of code. Now we just move things around. I mean, really, this and this were just put into the first and third sections. So that's looping, and that's one of the basic operations that are important in computer programs. So here's an example exam problem, and this is due as your second assignment, by the way. So take your answers to these, just put them in an email, send them to Jaron. CC me. So your problem is this. Here's the statement of the problem. When the code in figure 1 runs, when that code runs, what does it output to the console? All right, look at it. Look at this code. How many statements are there? Top level statements. How many top level statements are there? 2. 2. Very good. You got to think like this. That's the first one. That's the second one. And these statements run once. You know, we're not repeating the while loop. We run the while loop, and when we're done the while loop, we go to the next statement. And there isn't one. So the first statement declares an I, initializes it to 0. So you make a mental note. We have a variable I, and its current state is 0. Now this I can change. That's why we call it a variable. It varies, and its state varies. The number it's assigned to changes. So if you don't want to just make a mental note of I, make a box on your exam paper and label it I, and then write the number in the box that I currently equals. Just keep a record of what I equals. So don't forget what I equals. If you're going to forget, then write it down. I:0, something like that. Make a note. For this problem, it's not a big deal. There's only one variable. But if there's multiple variables, then you might need to keep notes about as you as you step through the algorithm, you may need to keep notes about what the variable equals. So now we do the while loop. So we'll look at the loop condition. If the loop condition is false right away in the beginning, we don't do the statements. We don't do the substatements. We're done. But the loop condition is true because I is less than 7. 0 is less than 7. So we're going to do the substatements. So the first thing we do, well, there's two operations here. So the multiplication operation has higher precedence than the output operator. So we multiply 2 by I, and then we get 0. And then 0 becomes the right-hand side of this output operator. We replace, this expression gets replaced by a 0. It evaluates to 0 currently. The next time we run it, it'll evaluate to something else. So this evaluates to 0, and that becomes the right-hand side of this output operator. And then standard output is the left-hand side of that output operator. So we're going to print a 0. So here's my exercise 2. I'll give it a TXT extension. So here's my what I'm going to submit to Jaren here. So the first problem. And I'll say, well, it's going to print a 2. A 0. And then what does it do? It increments I. After it prints a 0, it increments I. So I was 0, now I is 1. So remember, this is gone. This is finished. Forget about this. It happened. It's not going to happen again. I is now 1. So a lot of students, they forget about that. They look up there and say, oh yeah, but I is 0. This is not math. You know, I doesn't equal 0. I was assigned 0 in the past, but I has been assigned a new value now. I is something else. That's how you think about it. So when you look at this, I know the math people, they look at this, even non-math, everybody, the new people, they look at this and they say, well, I is 0. And they say, well, it's 0 forever. It's not. I was assigned 0, and it's changing. So I is now 1 because we ran this line. All right, now we're at the bottom of the loop. What do we do? Evaluate the, what?
You reevaluate your condition.
Reevaluate the condition. Very good. And so I, which is 1, is less than 7. That's true. That means we'll do the substatements. 2 times I, what's that? 2, because I is 1. We print 2. And increment I becomes 2. Reevaluate the loop condition. 2 is less than 7. 2 times 2 is 4. Print the 4. Increment I, that become 5. No, oh, I made a mistake. It was 2, now it's 3, right? So look, we're printing 2 times I, and I is going up to 7, right? So it's going to print 0, 2, 4, 6, 8, 10, right? That's where it's headed. Well, where's it going to stop? Well, what's the last value that I takes on such that the loop condition is true? 6. When I becomes 7, the loop condition is false. And we do not run the substatements. So we do not print when I is 7. But we print when I is 6. So that's the hair splitting that you have to do on the exam, right? If you're off by 1 and you print 14, then you get a 0 for this problem. There's no partial credit on these problems. All right? You gotta split hairs, you gotta be very precise. You know, roundabout isn't good enough. It has to be exact. So 12 will not print 14. Well, I'm going to warn everybody. This gets 0 credit on the exam. I know some students don't like that, and they complain about it. You know, when I get teaching evaluations, I say, the guy doesn't give any partial credit. It's very hard to give partial credit on this. This is just one. You know, it's not a big, complicated program. You know, if it was a big, large program, of course, there's partial credit. This is a very narrowly focused, simple exercise, and you got to get it exactly right. So it goes 0 to 12. And by the way, this is what I'm talking about now is called is an illustration of or an instance of the off by 1 problem. It's very common in computing to be off by 1. So if you if you think it prints 14, you're off by 1. All right, so it's just you'll see it as we go through the course. We're going to see lots of off by 1 issues come up all the time. And so that's where you have to slow up and think very carefully to get it exactly right. Because off by one can crash a program. You know, off by 1 can be a disaster depending on what you're doing. All right, there's some other things in here. Let me talk about this one here. This is integer division, and this is floating point division. This is 0.5, and this is 0. 1 divided by 2 is 0 because they're integers. So the compiler says, oh, that's integer division. So I'm going to give an integer result. So how does it take a half and shove it into an integer result? It just truncates. Remember, there's no rounding. So half, so if there's a numerator and denominator, both integers, the result is an integer. And we truncate, we discard, we don't round. But here, the numerator is an integer, but the denominator is a floating point value because it's a decimal point. So the compiler says, oh, you mean floating point division, so I'm going to give you a floating point result. So here the compiler will generate code, machine code that runs, it produces a 0.5 value. All right, that's that one. But this is the one that we need to talk about. This will be the last one we do today. So I equals 2. Integer k, you know, it doesn't work well when you copy and paste out of a PDF. I'm going to do it anyway. This actually might not compile. What's that?
You didn't establish that first high as an integer, so.
Oh yeah, I got to do that. Thank you. That's important, actually. All right, what does this code print? See, it does this. There's 3 statements. It does this one, it does this one, and then the third statement does output. Now, the right-hand side of the output operator gets evaluated first, and then the result is sent into the standard output stream, gets printed. So we're going to print one number. But what is that number? And well, the trick to this program to understand it is that there's a difference between I++ and ++I. By the way, this could be I minus 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 I as well. And this is a post increment, and this is called a pre-increment. So pre because the increment comes first. This is post increment because the increment comes after. After what? So this is an indication. This is a mnemonic to remind you. This is that the operation of increment. By the way, incrementing means add 1. Okay. Minus minus decrement. That means minus 1. Okay. So post, it means it's done after. After what? After what?
The line finishes running.
Huh?
That line finishes running.
Yeah, after this sort of whole line gets processed, we're going to delay incrementing I. We're going to use I. We're going to use I in the expression in which it appears. After we use I, then we're going to increment I. But here it's different. I is inside of an expression, but wait a minute. Wait, before we evaluate that expression using I, we're going to increment I first, and then we'll use I in the expression in which it appears. Here, it's the opposite. Let's use I right away. We're going to wait on the increment. Let's use I first in the expression in which it appears, resolve that, whatever it's used for, and then when we're done, we're going to increment I. So let's see what would happen here. I'm going to make some notes here. There's an I. There's an I, and there's a K, like this. Okay, so I, when we do the first line, it's very simple. We just create an I and we set it to 2. Now in the second line, we're going to assign something to K. But what do we assign to K? Well, we assign the result of this expression. What's the result of that expression?
Yeah.
4.
4. It's 4, because we're not touching I. We're not incrementing I. We're going to use I first. I is 2. So 2 times 2 is 4. And then 4 is assigned to K. And then, oh yeah, by the way, now that we finished that, let's go ahead and increment I. Right? After we use I, finish the statement, now we're going to increment I. Now I becomes 3. After K gets 4, I gets 3. Now we've finished this statement. It's sort of done in 2 steps. First we do it, and then we do the post increment. All right, let's do the next line. So this is the last thing we do, the output. The first thing we do is we evaluate the right-hand side of that output operator. But this multiplication has higher precedence than addition. So we want to evaluate this expression first. So what does that expression evaluate to?
8.
8. Everybody see that? Because we got to increment I first. I becomes 4. All right, we finished incrementing I. I is now we can use I after we incremented it. I is now 4. 4 times 2 is 8. And then 8 plus K is 12. So this expression produces 12. So we output 12. So the answer, is simply 12. Remember, that's either get all the credit for this or nothing. You got to get 12 exactly on the exam. That's it, right there. It's 12. I think that's it. The other things like summing, values 0 through n. Using a loop for that, you have to use a to sum 100 numbers. You need to declare some kind of an integer to hold the value, and you can use a for loop. What was that? 100?
Yeah.
So that loop runs exactly 100 times. And then it would just be sum plus equal I. See that? We want to calculate the sum of the first 100 integers. Was that the problem? 0 through n.
User puts an integer.
Oh, the user. And so this will be n. Does it include n? It doesn't say, does it?
No, it doesn't.
So you'd have to ask me in the exam, and I would say, I'm sorry, I forgot to say. And then go ahead and include it. So that includes n, and this excludes n. Right, so that's, I didn't get that. My question is not precise enough. See, this is an accumulator, this variable sum. You have to initialize it to 0. That's very important. In C++, uninitialized variables take on a random value. Most languages will initialize to 0, but C++, assembly language, those languages don't initialize variable declarations. So you have to be specific about it. You want to initialize it to 0. And then this plus equals, it just says whatever is in sum, increment, add to sum the value I. Don't replace sum by I. See, this says, that says replace sum by I. Assign I to sum. Replace sum by I. Well, this is, oh, don't replace sum by whatever's in sum plus the value I. Another way to write that is sum equals sum plus I. So these are equivalent. All right, I think that's it. Okay, well, so everyone has enough information to submit assignment 2 at this point.